Hi, I'm Tarek Alvi, and in this video I will be talking about the trebuchet and the physics behind it. I will do so in 3 steps. First, explaining the history of the trebuchet and the uniqueness of its design, followed by a more in-depth analysis of the design while applying several physics concepts to it, and then I'll end with an explanation of how changing a major component in the catapult can affect its ability to launch objects farther. To begin, let me go over what exactly a catapult is and the history behind this specific version. Merriam-Webster defines a catapult as an ancient military device for hurling missiles, and throughout history we have seen 3 main variations of catapults: the ballista, the onager, and the trebuchet. The ballista, which was the first catapult, was invented by a Greek ruler Dionysius the Elder in 399 BC, and was basically a large crossbow. It used the power of torsion and 2 pieces of twisted rope that would become twisted tight as a drawstring pulled the projectile back along a flat, angled plane. When the drawstring reached the back of the mechanism, it would be let go and the rope would rapidly unfurl, launching the projectile forward. The onager was more similar to a trebuchet, but it also relied on torsion as the firing arm was inserted into a piece of twisted rope in the center of the machine that would become twisted tight as the firing arm got pulled backwards to the ground. After being released, the firing arm would rapidly swing up in a 90-degree motion and hit a crosspiece that would send the projectile and the bowl flying. However, the most powerful and arguably the most well-known catapult of the medieval times was the trebuchet. There are actually many different types of trebuchets, like the mangonel, which required a team of men to pull ropes on the short end of the firing arm, which would launch the projectile. But the model that I'm going to be exploring in this video is the counterweight trebuchet, which uses a large weight on the short end of the firing arm to propel the projectile out of the sling. It's a bit uncertain who invented the trebuchet, but the earliest known description of one comes from texts written in 1187 by a military writer named Mardi ibn Ali al-Tarsuzi. There have been other reports of this specific model's existence prior to this treatise, but all of those claims are largely uncertain. During the following centuries, the counterweight trebuchet became one of the go-to strategies for besieging fortresses and towns surrounded by protective walls. This was mainly because of its incredibly strong power and intimidating size. To demonstrate the trebuchet's design and firing mechanism, I have constructed this small prototype. There are 6 parts of a trebuchet. There is a frame, which supports the firing mechanism. Then in the firing mechanism, there is the firing arm, which is connected to the pivot in the middle. It's connected to the pivot in such a way that there is a long end and a short end of it. On the long end, there's a hook, which the sling is attached to, and the sling is what carries the projectile. On the short end, there's a massive counterweight that is hanging from a short string that drives the entire firing motion of the catapult. To fire the catapult, you simply place the sling on the hook and hold it down underneath the firing arm. Make sure that the string is taut, and then let go and watch the whole thing unravel. Now you might be wondering why the counterweight is hanging from a string instead of being in a fixed position on the firing arm. This actually improves the length that the projectile can be fired from the catapult due to a concept called sling stall points. In order for the projectile to launch effectively, it can gain a little more lift if the sling suddenly stops moving in the middle of its motion, because it allows the projectile to swing around the hook more efficiently. On a trebuchet, this effect can be achieved when the counterweight is hanging from the firing arm. The counterweight will drop straight down in free fall, and when it reaches its lowest possible point, the string attached to it will try to follow its downwards motion, but be restricted by the naturally circular motion of the firing arm since it's connected to the pivot. So this leads to a sudden jerking motion and a brief stop of the entire mechanism, like so. There are 3 main physics concepts that are part of this process. The first one is tension. It plays a crucial role in the trebuchet because the sling is pulled and held in place to get the counterweight to its highest position. It's also present in the string that attaches the counterweight to the firing arm, whose force of tension can be calculated using the equation mass times gravitational acceleration plus mass times acceleration. But since it's at rest in this position, its acceleration is zero, so it's only limited to gravitational acceleration times mass. According to these calculations, the force of tension for the counterweight string in my model is 0.235 newtons. The second important concept is torque. The definition of torque is essentially the force that drives the acceleration of an object around a central axis. Think of a door swinging around on its hinges. The hinge is the central axis and the door is the object accelerating around that fixed point, making it the most accessible example of torque in our day-to-day lives. In the trebuchet, the entire mechanism is based around the acceleration of objects connected to the central axis, the pivot, making torque very important in the mechanism. Torque ties into another important physics concept, which is the forces of motion. The entire mechanism is powered by the force of gravity. In my models, there is a lot of friction because realistically there cannot be friction in this movement. However, for simplicity's sake, we're going to say that there isn't any friction in these models. The force of gravity can be calculated through Fg equals mass times acceleration of gravity. So the force of gravity on this counterweight would be 0.235 newtons. The final concept is the storage of energy. As the sling is pulled under the frame, the gravitational energy in the counterweight begins increasing. This gravitational energy then becomes kinetic energy as the counterweight falls, pulling the firing arm, the hook, and the projectile in the opposite direction until it reaches its stall point. The gravitational energy that drove the projectile upwards from its initial position then propels it off the hook and in the direction that it was being carried around the hinge, forward. In terms of the physics of how the trebuchet actually launches projectiles, I've come up with a series of calculations and diagrams based on information given by Mr. Ciano's article. Here, we have a diagram of a very simple trebuchet. There are multiple variables here such as MB, which represents the mass of the firing arm, L1 and L2, which represent the long and short lengths of the firing arm, and the height of the frame as lowercase h, the height of the counterweight from the ground as uppercase h, and the masses of the counterweight and projectile are m1 and m2 respectively. Finally, theta is the angle formed between the firing arm and the ground before the catapult is fired. Since I'm trying to answer the question of how changing the counterweight's weight affects the range, I will be assuming that all of the variables except for m1 and m2 remain constant. Before we get to the actual calculations, I'm going to quickly define some variables. So we're going to let m1 be the counterweight mass, m2 will be the projectile mass, v naught will be the initial velocity of the projectile, lowercase t will be the time traveled by the projectile, and finally, capital R will be the range of the projectile. This diagram represents the velocity vector of the projectile as it's being launched from the catapult, with theta representing the angle that the vector makes with the ground. The vector itself can be easily calculated by being broke up into v naught cosine theta for its horizontal travel, and v naught sine theta for its vertical travel. I will try to calculate the maximum range of the catapult using v naught and equations relating to the conservation of energy. Firstly, we can find the horizontal range by using v naught cosine theta times t. That's our first equation. The next step of the process is calculating the vertical range, using one of the big five equations and substituting those variables with the ones we use in this situation. One thing we know for sure is that the velocity of the projectile at its highest point is 0 meters per second, so v2 in this case would be 0. And since it's in free fall, the only acceleration would be that of gravity. Now we isolate for t so that we can substitute those values into the first equation. With this combined equation fully simplified, we can move on to calculating how the masses of the projectile and the mass of the counterweight affect this velocity vector. Under the assumption that there is no energy lost, the gravitational energy gained by the counterweight should be equal to the kinetic energy of the moving projectile, since the trebuchet uses a lot of lever physics in its motion. What we're trying to do here is isolate for v naught squared so that we can substitute this into the range equation. So the maximum range equation for a trebuchet is 4 times mass of counterweight times height of counterweight times sine theta times cosine theta divided by the mass of the projectile. Plug in the values that we measured already, and we get a maximum range of 16 meters. Now that we know how each part of the trebuchet works in terms of its design, as well as the physics behind it, we can answer the ultimate question. How can changing the weight of the counterweight affect how far the projectile can be launched? I'll be demonstrating this using the classic fixed counterweight model of a trebuchet. Here we have a trebuchet whose counterweight consists of a single battery. According to this series of tests, it has an average maximum range capability of 53.5 centimeters. With this in mind, here's a trebuchet whose counterweight consists of two batteries. As you can see from these tests, the average maximum range capability of this version is 64.5 centimeters, which is higher than the average maximum range capability of the other model. This happens because of the ratio between the weights of the counterweight and the projectile. In his 65-page scholarly article Trebuchet Mechanics, Daniel B. Ciano formulated a set of instructions for the design of the most optimal model of a trebuchet in terms of what he called range efficiency. These instructions included the recommendation of having a 100-to-1 ratio between the counterweight and the projectile. Anywhere below this ratio will result in a poorer range efficiency, but anywhere above it doesn't improve it that much either. As you can see on this graph from Mr. Ciano's paper, the effectiveness of increasing the weight of the counterweight begins plateauing after a certain point. Mr. Ciano also notes that having a firing angle of 45 degrees will help increase the range efficiency of the trebuchet, which is why I subbed it into my equation while calculating the maximum range. Now you might be wondering why my results from my real-life tests were so different from my calculations. This is due to a number of factors. For one, I made a lot of assumptions at the beginning of my calculations, saying that all of the variables except for the mass of the counterweight were to be considered consistent. In real life, however, pretty much all of these preset parameters were constantly shifting, since real models can't be as perfect as what's described on paper, especially when they're made out of popsicle sticks and pencils. Another factor is the fact that I assumed that all of the energy would be conserved and transferred within the structure of the catapult, but in real life, some of that energy would be lost because the frame isn't planted securely in the ground, meaning that the swinging motion of the firing arm will cause its platform to move a little, resulting in a loss of energy due to friction. On top of that, the projectile being launched is probably one of the least aerodynamic objects that could be launched from a catapult, so air resistance would definitely play a large role in hindering its range capabilities. Lastly, one of the key factors in the calculation was the angle between the firing arm and the ground staying 45 degrees. Play back the recordings of the tests, and you can see for yourself that this angle was constantly changing. In a nutshell, increasing the mass of the counterweight can increase its range efficiency only up to a certain point, but in real life, it really depends on how strictly you control the environment. In this video, you saw me talking about the trebuchet and the physics behind it. I did this by explaining the history of the trebuchet and the uniqueness of its design, followed by a more in-depth analysis of the design while applying several physics concepts to it, and then ending with an explanation of how changing the weight of the counterweight in the catapult can affect its ability to launch objects farther, where I reached the conclusion that increasing the weight of the counterweight will be helpful to the range efficiency of a trebuchet only up to a certain point, after which its effectiveness will plateau, even though in real life its effectiveness can vary depending on how controlled the environment is. Thank you for watching, and I hope you learned something new.